All right, so this is the first screencast for the nuclear chemistry unit. So our essential question is, what causes some nuclei to be radioactive and others not to be? So why are some nuclei going to be unstable and others are not? So first of all, we have to talk about what is radioactivity. So radioactivity is the process by which atoms emit energetic particles or rays. So they're going to give stuff off. A lot of times we think of things being unstable, so they're going to lose things to make them more stable. So we end up with changes in the nucleus. This is the only time that we will see changes in the nucleus. We are actually going to change proton numbers. Any other time we've done any type of chemical reactions, those involve electrons and the movement of electrons. Isotopes involve neutrons, but in this case, radioactivity, we are going to be changing neutron number or proton number. So we have to review nuclear symbols and isotopic notation. Remember, isotopic notation includes the atomic symbol, the atomic number, the atomic symbol, which is just the element symbol, atomic number, which is the number of protons, and then the mass number, which is protons plus neutrons. So this should look familiar to you. So having the symbol of the element, the number that goes on top is the mass number, and then the number that goes on the bottom is the number of protons. And remember, mass is protons plus neutrons. So we're going to be working with this a lot. We're going to be working with isotopic notation a lot. So for example, there's 3 isotopes of carbon. There's carbon-12, which is this, carbon-13, which is this one, and carbon-14, which is this one. Carbon-12 has 6 protons and 6 neutrons in the nucleus. Carbon-13 still has the 6 protons, but now 7 neutrons, and carbon-14 still has 6 protons, but now 8 neutrons. As we change the number of neutrons, we change the stability. So with different numbers of neutrons, the mass of each isotope is different, and we also change the stability. In that particular example, carbon-14 is radioactive. It's unstable. So what makes something unstable? An unstable isotope or an unstable nucleus, these are the ones that produce radioactivity. Stable nuclei will not give off radiation. And that process, the transmutation process, happens when an unstable nucleus loses energy by emitting radiation. And this is called nuclear decay or radioactivity, and it can give out the material, how it's going to lose energy or the radiation. It can give it out in the form of waves or particles. So like down here, it can give it out in the form of waves, which are called gamma rays. And then it can give it out in particles, which are the alpha particles or the beta particles. So the energy that comes off tends to be ionizing, which is very high energy. It actually, this energy, these gamma rays can kick off or knock off electrons from other atoms. It can damage tissues and damage DNA, so it's not the good type of radiation to have. The non-ionizing stuff causes vibrations of atoms and electrons, but not the loss of electrons, like radio waves and microwaves. So we're talking on the gamma ray end of things, X-rays and gamma rays. So here's just a little chart showing you radiation doses and their health effects. So if you look at the very bottom, the annual radiation from living within 50 miles of a nuclear power plant, it's also the radiation dose from eating a single banana. So all of us, we live within 50 miles of a nuclear power plant, so we're getting a little bit of radiation, millirems, 0.01 millirems every year. If you live within a coal-fired power plant, you actually get more radiation exposure, which is kind of interesting. The daily additional radiation in Tokyo, Japan from fallout of the Fukushima disaster, that reactor failure that happened in 2011. And then as you go up, the annual radiation, including background radiation on the Bikini Atoll site, the U.S. nuclear weapons site in the 1950s. This is how much instant radiation you get from an abdominal CT scan. So you get 1,000 millirems from a CT scan. The average yearly radiation for a typical U.S. citizen is about 620 millirems. So everybody is exposed to some radiation. When you start getting up into this amount, though, this is when it starts getting dangerous. The total radiation of exposure of plant workers and firemen at the Chernobyl disaster in 1986. I mean, this is why people died. The instant radiation exposure causes internal bleeding, destruction of the intestinal lining, and death within 2 weeks at this level. So when you start getting up into here, you get some serious damage to the tissues because of the gamma rays. So total radiation exposure over time associated with high risk of leukemia, bladder, breast, colon, liver, lung, esophagus, stomach, and ovarian cancers, kind of in this range right here. So I find this one always interesting. 5,000 millirems is the annual safety limit of radiation exposure for people who work with radioactive material. So the peak hourly radiation exposure of plant workers at the damaged Fukushima site were getting this much per hour, and this is how much you're supposed to get safely in a year. So they were exposed to a lot of radiation. So just some, kind of ideas of how much radiation you're exposed to. So all of the elements above number 83 on the periodic table, they're called the trans-uranium elements because they come after uranium. They are all radioactive. So 84 through 118 are all radioactive. What makes something radioactive again is that unstable relationship between the number of protons and the number of neutrons. So less than 20, they tend to be, if your element number is less than number 20, so 20 and below, they tend to have a 1-to-1 ratio of protons to neutrons, and that makes them more stable. The closer your proton and neutron number is, the more stable that nucleus is. But as you get above element number 20, you start to lose that kind of 1-to-1 ratio, and you get more to a 1-to-5, or even a 2-to-1, or a 3-to-1 ratio, but in terms of the number of neutrons to protons. And it becomes less stable at that point, because you end up with more neutrons than the atom can handle. So if the ratio becomes too high, meaning you have too many neutrons, the nucleus becomes unstable, and now it has to try to make itself stable. So it's going to emit radioactive particles out of the nucleus to gain that stability back. So you're going to lose stuff out of the nucleus, whether it's alpha particles or beta particles or gamma radiation. It's going to start to lose things, and that's what makes something radioactive, is if the ratio between protons to neutrons gets too high. So there's 4 types of ionizing radiation. We're not really going to talk about positron particles, but we're going to spend most of our time talking about alpha, beta, and gamma rays. So an alpha particle, it is an actual particle. It has mass. The notation for it is an alpha symbol, so the Greek letter alpha, or you might see it as a helium atom because it is 2 protons and 2 neutrons. So an alpha particle is equivalent to a helium nucleus in size. It has a mass of 4 and atomic number of 2. So it can be shielded by paper, though. So you can, if somebody's shooting alpha particles at you, a piece of paper is going to stop it. Beta particles, on the other hand, are much smaller, but they're more dangerous. Beta particles, the symbol for them is a beta, and we're going to talk about what they are and how they form. But beta particles are essentially a neutron decomposes into a proton and an electron. And then they can be stopped by aluminum foil. Gamma rays, however, though, you notice there's no mass to them. There's no charge to them. Gamma rays are energy, so they're just electromagnetic radiation waves. And they can be stopped by lead or by concrete, which is why when people built bomb shelters, they surrounded them in concrete with, a few centimeters of lead going through the center of it. And even that doesn't stop it 100%, but at least it does stop some of it or most of it. When you go to the dentist and they take an x-ray of you, they put a lead vest on you to protect you. It's the same concept. It doesn't stop all of it, but it does stop a lot of it from penetrating. So let's talk a little bit more about each one of these. So alpha particles, here's the symbol again. Here's all of these mean the same thing. You can just write alpha particles like this. You can write alpha particles as a helium atom. You can write alpha particles as a helium atom with a 2+ charge. An alpha particle is the least dangerous in terms of that external exposure. It does contain 2 neutrons and 2 protons, so it's the biggest. So if an atom is going to become stable by getting rid of an alpha particle, it is going to give off 2 neutrons and 2 protons. These can't penetrate very deeply into the skin because they are so big. So a piece of paper or clothing will stop alpha particles. But once ingested, though, so like, for example, radon, if you ingest them, alpha particles can be very dangerous because then they're right next to the tissue. They're not trying to penetrate through. They are actually right next to the tissue and can cause a lot of damage. So even though they don't typically cause radiation sickness, instead they tend to lead to lung cancer because you're going to be inhaling them. For example, with radon, you're going to be taking them in from the outside. Uranium decomposes to radium, decomposes to radon, and then that radon can filter into your house. And that's why some people have radon detectors, or they get their house tested for radon levels. Beta particles, on the other hand, as you can see here, a beta particle is when a neutron decays into a proton and electron. So you lose a neutron, but you gain a proton, you gain an electron. So it's the same as an electron. It's given off when a neutron turns into a proton. We're not going to worry about positrons. But it's blocked by most solid objects like aluminum foil, wood, plastic. It can penetrate clothing and skin, but it is blocked by some things. It's about 8,000 times smaller than an alpha particle, so that's what makes it a little bit more dangerous. External exposure can cause burns and tissue damage, along with other symptoms of radiation sickness. But internal exposure definitely has more severe symptoms, and a classic example of beta radiation or beta particle radiation is carbon-14. It goes through beta radiation. So the cosmic radiation, the cosmic rays enter Earth's atmosphere and collide with an atom, creating an energetic neutron. That neutron then bombards other elements. So when that neutron collides with a nitrogen atom, a nitrogen-14 atom turns into a carbon-14 atom, and then that carbon-14 is absorbed by living organisms because all living organisms are carbon-based. Plants absorb carbon dioxide and incorporate the carbon-14 through photosynthesis. Animals then collect it. Following death and burial, wood and bones, they lose the carbon-14 as it changes back to nitrogen-14 by beta decay. So it goes through beta decay to become nitrogen-14 again, and then that process can start all over again. Gamma rays, these are actually not a particle. These are just high waves of waves of energy with with a lot of energy with them. Most dangerous form of ionizing radiation, it's extremely high energy photons, so it's just light particles that can travel through most forms of matter. They have no mass. Stopped by several inches of lead or several feet of concrete. Exposure will pass through the entire body, and it'll affect all of your tissues from your skin to the marrow of your bones, and it causes widespread systemic damage. So if you were to be exposed to something, gamma rays would not be it. Just a little bit about positrons. Positron has the same mass as an electron or a beta particle. It's just going to have the opposite charge. Like I said, we're not going to worry about positrons too much. So here's something I want you to draw down in your notes, kind of the penetrating ability. Alpha particles are stopped by paper. Beta particles are stopped by aluminum. And gamma rays would go through all of those and then be stopped by lead, or at least the majority of them would be stopped by lead. So that concludes your first screencast for nuclear chemistry.